Hello everyone, Kotongana, the Nature God here. This video is going to be based on how to solve problems based on Venturi meters. Right now, Venturi meters are essentially part of the topic measurement of flow. Specifically, a Venturi meter is essentially an instrument that is used to measure flow. Right, so you will find Venturi meters under the topic of either measurement of flow or flow measurement using instruments, right? Now, Venturi meters, right? Like I said, it's a topic that's a part of measurement of flow, just like flow through an orifice. So you're gonna see some of the formulas. In fact, most of them are relatable to flow through an orifice, right? Now, let us look at this diagram. We have a pipe, right? The pipe is fitted with the Venturi meter. The Venturi meter is the blue one here, right? So here is the pipe, which is the inlet, right? And then this here, which is labeled as 2, is the neck of your Venturi meter, right? Now, Venturi meters are used sometimes in conjunction with manometers, right? So here is a manometer, and a manometer is an instrument that is essentially used to measure the pressure difference, right, between any 2 points in the fluid's motion. So if the fluid enters from this side, which is the pipe side, right, this will be the inlet. And then if you look at the other column, or where the other part of the manometer is fitted on the neck of the Venturi meter, right? So essentially, in this scenario, the manometer is measuring the pressure head difference between the pipe and the neck of the Venturi meter, right? Now, in fact, for fluid mechanics, right, because I remember in N4, in mechanotechnics N4, the fluid that is used to measure the what is this thing? To measure the pressure head difference between the inlets and outlets, right, or between the 2 points that are of interest, was filled with mercury, right? So you can disregard this mercury here, right? In fact, if you look at both diagrams, one has water inside the manometer, the other one has a mercury, or is a mercury manometer, right? That is to say that it's not always the case that mercury is used or that water is used. The reason why we do use mercury, though, is for the fact that when having to use a different fluid, they found that the reading of the pressure head difference between the 2 points of interest, right, isn't quite accurate, or isn't as accurate when having to use a mercury manometer, right? Even with the mercury manometer, right, it isn't quite accurate, right? That is why they then came up with this formula, right, to calculate the pressure head difference between the inlet and outlet. That formula is, so the pressure head difference, right, of the fluid running through the pipe and the what is this the Venturi meter. So if, for instance, the fluid running through the system is water, so this would be the pressure head difference, right, of the water between point 1 and point 2 is equal to, and then the formula then is the H of mercury. So Hg is how we denote mercury, right? So the head of mercury, right, multiplied by let's see here, let's change this to weight. So multiplied by the density of mercury divided by the density of the fluid running through the running through the hydraulic system. So this would, for instance, be the mercury of water, right? If indeed it's the water that's running through the system, right? And then minus 1. Right, this is the original formula that we use to calculate either the pressure head difference or the head of mercury. Right, this is the formula we use. Now to simplify this formula, right, the density, let's say here H of water is equal to HHG times, now the density of mercury, right, remains the same. It is incompressible, hence it remains the same. It is always, or we can always take it as 13,600 kilograms per cubic meters, and then the density of water we take as 1,000. Right, now if you punch this in your calculators, you should get 12,6, and then that 12,6 times the HHG means that the H of water will be equal to 12,6 HG. Right, let's make this small letter H, HG. Right, this formula you probably are familiar with. Right, it is just interesting to note that this is where it comes from. Right, so for measurement of flow, right, if you want to measure flow, you are able to use this formula, right, for any kind of fluid that you're looking at, including air, including gases. Right, so if you're looking at a gas, then you should take note of that. You should be given the density of gas, or you should be given enough data for you to be able to calculate the density of air or of gas, right? But you are also able to use this formula to calculate the pressure head difference, right? Using this formula, the only difference is that now the pressure head difference will be the pressure head difference of air, and this here will be the density of air. Right, also you should take note that if air is being used, it means you are looking at a pneumatic system. Right, so for hydraulics or for in fluid mechanics, we get hydraulic systems, we get pneumatic systems. Right, and those systems use different fluids, right, for different reasons. Right, to cut the long story short, for hydraulic systems only make use of fluids that are incompressible. Right, so they only make use of fluids that are incompressible for the system to be able to do work, whereas pneumatic systems make use of fluids that are compressible, so essentially gases. Right, that is just for interest's sake. Now that is where this formula comes from. Right, now like I said here, the inlet, because the inlet of the fluid is on the pipe side, so D1, right, so D1 is the pipe diameter, and then D2 will be the throat diameter, or the diameter of the throat of the Venturi meter. Right, now I did explain that this H here, right, this H is essentially the pressure head difference, which if you were to apply Bernoulli's between these 2 points, right, this would be equal to the HW would be equal to the pressure head difference. By pressure head difference, that is P1 minus P2 divided by rho g. Remember that to calculate the pressure of a fluid at any point, the general formula for that, or the pressure energy, right, is rho gh. So if you're looking for h, you obviously have to get rid of the rho g, right, by dividing by its both sides. Hence, in terms of the pressure head difference, so the difference in pressure between point 1 and point 2, essentially this is what you'd get. So essentially the pressure head difference would be your HW. Right, so your pressure head difference is what has been denoted here as HW. Right. Right. So HW is your pressure head difference, and then HHG is the head of the manometer. Right. That's one of the formulas to take note of. Another one would be this one, Q. Right. What is this thing? Let's see. From what is this? Flow through an orifice. We know CD is equal to QA divided by QT. That's the actual discharge divided by the theoretical discharge. Right. So essentially, if you're looking for QA, right, QA would then be equal to CD times the theoretical discharge. Right. This we know from flow through an orifice. Right. That is to say that now for Venturi meters, to get QA, which is the actual discharge, right, the actual discharge will be equal to CD times QA. So this will be CD times, now QA, I mean not QA, QT, which is the theoretical discharge. It is equal to the area of the pipe, so A1. Remember that A1 here represents the area of the pipe, which is the inlet, times the square root of 2GHW divided by the square root of, let me do this, square root of, what is this, D1 to the exponent 4 divided by D2, which is the throat diameter, to the exponent 4, right, minus 1. Right, and this here is the formula you use to calculate the actual discharge, right, of the water through the hydraulic system. Right, where of course this is the coefficient of discharge. Like I said, the area is area 1, which is the area of the pipe. D1 is the diameter of the pipe. D2 is the diameter of the throat, or the throat diameter, and then HW is the pressure head difference between point 1 and point 2. Right. So remember that area is equal to pi over 4 times d squared. Right. So because this is A1, it means the D would be D1 here. Right. Right. Every other formula that applies here, you are already familiar with. By that I mean how you calculate Q. Right. We know Q is equal to area times V, and then also the continuity equation. We know that the Q, or the flow rate in a pipe, be it a pipe with a constant diameter or a tapered pipe, right? As long as the pipes are not parallel, right? As long as the pipes are not parallel, then the Q, right, the Q at inlet will be equal to the Q at the outlet. That is the continuity equation. And then, of course, the application of Bernoulli's equation, be it you are considering losses or not. Right, that is what I mean by the other formulas that are applicable here. We are already familiar with. Right, I just want us to look at an example of an exercise based on Venturi meters. Right, reads as follows: a Venturi meter with a throat diameter of 140 millimeters is in a pipe with a diameter of 230 millimeters. The discharge rate of the pipe is 120 liters per second. Use a coefficient of delivery of 0.96. That CD. Assume that the Venturi meter has a mercury manometer. Right, calculate the mercury head in manometer. Right, they want us to calculate the mercury head. Right, one thing we have established here is that we typically have two heads. That's the pressure head difference, which is HW, and then we also have the mercury head, which is HG. Now here they said calculate the mercury head, so it means this is what they're looking for. They're looking for HG. Right, so let's write down what we've been given. So as far as what we've been given, they said Venturi meter with the throat diameter of this. So we have the throat diameter. Throat diameter is D2, right? And then the pipe diameter is 230, so which means D1 is equal to 0.23 meters. And then throat diameter, so D2 is equal to 0.14 meters. Right, the discharge rate of the pipe is 120 liters per second. Right, when you've been given quantities like velocity of the fluid in the pipe, or the discharge or the flow rate of the fluid in the system, right, we always assume that the quantity you've been given is the actual. So that is to say that if they say that the discharge rate, you've been given the discharge, absolutely nothing suggests that this is the theoretical discharge. So you of course take it as the actual discharge, because remember that the theoretical discharge is only used under ideal situations. Right, so unless they've stipulated that the quantity that's been given is theoretical, you always assume that it is the actual. Right, so our discharge here has been given as liters per second. Right, in our calculations you must always use the standard units of measurement, and the standard unit of measurement for a flow rate is cubic meters per second. So this you have to convert from liters per second to cubic meters per second. So that is to say that you divide this by 1,000, converting liters to cubic meters. So 120 divided by 1,000 equals 0.12. Now this is in cubic meters per second. We've also been given CD, and CD is 0.96, and then they want us to calculate HG. Right, they want us to calculate HHG. Right, from here it's essentially the application of formulas. Right, knowing that essentially these are the formulas, right, that you are going to use here. Right, you have to decide which one is going to be convenient for you to use based on what it is that you're looking for. To get what we are looking for, right, think about the only formula that you can use to get what we are looking for. We know to get what we are looking for, we have to use this. Right, we have to make use of this relationship. Remember here, they did mention that assume that the Venturi meter has a mercury manometer. Right, so the Venturi meter is using a mercury manometer, which means the H is HHG. So in order to be able to calculate this H, it means we must have the pressure head difference between 0.1 and 0.2. Now, you then have to look at your scenario, look at your given data, and decide the best approach to take. Now, in order to be able to apply Bernoulli's, remember that Bernoulli's equation, whichever variation of Bernoulli's equation that you use, you have to make certain that you have at least three energies. Right, that's pressure energy, right, that is kinetic energy, and that is potential energy. Right, aside from frictional head losses or losses in the system. Right, those are the three main energies that you have to look out for. Right, with kinetic energy, we know we are going to need velocities, which we do not have here. With potential energy, we need the H's. We don't really need the H's here. Right, and then with with the pressure energy, right, we need the H's. Not really. You can always manipulate Bernoulli's equation such that you have the pressure head difference, hence the HW, but then you will have two unknowns, right, because you all know the velocity. Remember, we haven't been given the velocity here. You've been given Q, so even if you use the continuity equation, you still have two unknowns, V1 and V2. Hence, you'll have to express one of the velocities in terms of the other, and then having to substitute it into Bernoulli's equation. It means that you are going to have two unknowns, right? For instance, say in using the continuity equation, you decide to express V1 in terms of V2, right? So in Bernoulli's equation, for your kinetic energy, V1 will be expressed in terms of V2, and then V2 will be expressed in terms of V2, right? So it eliminates one of the velocities between V1 and V2, but there's still the HW, which will be the pressure head difference between 0.1 and 0.2. So essentially, you will have this as an unknown, and also V2 will be an unknown. Right? So which means you cannot take the approach of the application of Bernoulli's. Right? Another approach, which is the best approach, looking at the data you've been given. You've been given QA, right? You've been given CD. You have both the diameters, so which means you can use this equation here, right? From this equation, you have QA, you have CD, you have the areas, you have the diameter. The only unknown is HW. Once you get HW from this formula, you then go back to this one to calculate HG. Right? Simple, straightforward. So from here, right, so remember we had established that this is the formula we need to use to calculate this, seeing that this is what we're looking for. But now to get this, we need to have this, we have to take this approach to calculate. Right, so now from here you then substituting QA is 0.12, 0.12 is equal to CD. CD is 0.96 times the area, which is pi over 4 times D1. Remember, this is area 1, so D1, which is 0.23 D1 squared times this here. So you have this, right, times 9.81 times HW, right, and all of this divided by the square root of the square root of D1, which is 0.23 to the exponent 4 divided by D2, which is 0.14 to the exponent 4 minus 1. Right, now obviously from here, how you proceed mathematically is going to be up to you. I'm going to try and take this step by step so that you don't get lost. Right, but like I say, from here mathematically, it is up to you how you proceed, because essentially from this point, fluid mechanics is done. Right, it's just a matter of how you understand your math. So here, your 0.12 is equal to, now if you punch all this in your calculators, right, we get 0.0399. Right, to make things simple, remember that essentially all this is one term, because this, right, it is being multiplied with that, making essentially this the same thing. Right, it's essentially one term because this is a product. Right, so which means I can just simplify the denominator here and then divide this by the denominator. So if you punch this in your calculators, the square root of all of this, right, so you're gonna have the square root of, right, the square root of what is inside. So you are going to calculate, or this approach that I've taken here is calculating what is inside the brackets, right, which is equal to 6.2845. Right, right, and then the numerator, which is this, right, if you calculate what is on the inside, so the 2 times 9.81, we are going to get the square root of 19.62 HW, which is the pressure head difference between 0.1 and 0.2. Right, then from here, if 0.12 is equal to, starting with this, now if you punch this in your calculators, so this divided by everything in the denominator, we get 0.0159. Right, so let me just confirm this quickly. Yeah, so this is what I have on my calculator, times this here remains the same, and so times this, and then of course we are looking for HW so we have to get rid of everything else. So first I'm going to get rid of this by dividing by its both sides. So that's 0, 0,0159, 0,0159. That cancels, and then you're left with this. Now this I'm going to put on the right hand side for convenience, is equal to what is on the left hand side, which is this. Right, now I get rid of the square root, right, by applying a square on both sides. So the square of this cancels the square root, which means you'll be left with 19,62 HW is equal to the square root of, not the square root, sorry, the square of, so this will be 0,12 divided by 0,0159 squared. All right, I trust this is what everyone has. All right, then we have 19,62 HW is equal to, and then if you punch this in your calculators, you should get 56,9598. And then because I'm looking for HW, I then divide by this coefficient, making sure that the coefficient of HW is 1. So 19,62, 19,62. That cancels. Therefore, HW is equal to, then of course you punch this in your calculator, and you should get 2,903. And because this is H, we know it is in meters. Right, we are confident that this is in meters because all the quantities we've used here, we've used in their standard units of measurement. Right, once you have your HW, now you can calculate your HHG. We know HW is equal to 12,6 HHG, which therefore means to get HHG, you have to divide both sides by 12,6, and then HHG will be equal to the H of water divided by the 12,6, and then when you substitute, you have the 2,903 divided by the 12,6. Right, and then if you punch that in your calculators, you should get 0,230 meters. Right, or if you want to express this in millimeters, then this would be 230 millimeters, and this here will be your HHG. Right, this is just a typical exercise based on Venturi meters, right, that shows you how you would apply these formulas. Right, the key formulas here, right, are these two, this one and this one. Right, because all the other approaches you're already familiar with, that is the application of Bernoulli's. If say you've been given the what is this thing, you've been given Q and you have to calculate V, right, you can use the continuity equation and then apply Bernoulli's, right, and then from Bernoulli's you can get the pressure head difference, which will be that P1 minus P2 divided by rho G. Right, the point here is I did this one to highlight the two key the two key formulas for Venturi meters, because all the other ones or all the other approaches are similar to the ones we take when looking at flow through an orifice, right, or any other exercise based on instruments for measuring flow. Right, I hope you found this helpful. Stay tuned for more videos.